4.1 Maximum and minimum values. Essential question: how does a derivative reveal the extreme values? An absolute maximum is defined to be the y value in which it's the greatest or equal to all others in the domain. An absolute minimum at x equal to c is such that that y value is the least or equal to everything else in the domain. These are called extreme values. A local maximum is going to be the y value that's the highest, that's near c, and we have to have an open interval containing c in order for this to be a local max. Here are some examples right here with our minimum value f of a and our maximum value f of d. In more detail, we would call f of a an absolute min. At c, we would call it a local min. At e, we would call this a local min as well. At d, we would call this a local max because f of d is the highest y value, just as f of a here will be the smallest y value. And at x equal to b, we have a local max. Let's take a look at a trig function. In a trig function, we have the local max and min being at the same location. And we also have an infinite number of these absolute max and mins, and we can write it this way, where we locate all of these maxes and maxes. Now for the minimum, it's right here at x equal to pi, and then we encounter other local mins and absolute mins if we write it in this form. Let's take a look at y equal to x squared. We notice that y equal to x squared, we have an absolute minimum value, but no maximum. If we take a look at y equal to x to the third power, we notice that we have no minimum or maximum values. An absolute maximum, remember, is not a local max because it occurs at an endpoint. So right here, this point right here, is not called a local max. In order to be local, you have to be in an interval, and since it's at endpoint, it's not. Now this point right here is an absolute max. Absolute max may occur at the endpoints. This point right here is a local min. This point right here is a local max. And this point right here is a local min, and at the same time it's an absolute min. So you can see sometimes the absolutes occur at the endpoints and sometimes they occur in the interval. The extreme value theorem says if f is continuous on a closed interval and if f attains an absolute maximum value, it will attain an absolute maximum and an absolute minimum value at some numbers. So here's an example. Again, you have to meet the conditions of continuity. So when you have continuity, notice that your absolute max can occur in the interval, and it looks like your absolute min occurs within the interval. Over here, the absolute min occurs at the endpoint, the absolute max occurs in the interval. And over here we have an example of maxes and more than one, and here's an absolute minimum. Now right here we have an absolute minimum, but we don't have an absolute maximum, and that's because we don't have continuity. You must have continuity in order to guarantee that you have both. In this one, we have neither absolute min or max, and that's because, again, it is not continuous and it's not a closed interval. You must meet both conditions in order for this to happen. Fermat's theorem, if f has a local max or minimum at c, and if f prime of c exists, then that derivative must be equal to 0. So let's take a look at it with a maximum. If we choose 2 points very close to this point, right here, and we find the difference quotient, we're going to find that, well, let me go to the other side, over here. If we go from here to here, we're going to find this slope is slightly less than 0. And when we go from this side, we're going to have the difference quotient slightly more than 0, because see, the slopes are positive in this direction but negative in this direction. But as h approaches 0 from the right hand side or from the left hand side, these limits are getting closer to the same number, which is 0. And this proves, this portion right here, that the derivative must be equal to 0 at c. And this case is also true for a local min. All right, let's take a look at the cubic function. Let's find its derivative, set its derivative equal to 0. So what we're looking for is horizontal tangents here. And we can see that occurs here at 0. So in this case, the first derivative at 0 is equal to 0, but we don't have a maximum or a minimum. Let's also take a look at the absolute value. Notice that the absolute value can be defined this way, and its derivative will be equal to 1 if x is greater than 0 or negative 1, and there is no value for a derivative at 0 because we don't have that limit situation happening, so it does not exist. And yet, this value is an absolute minimum value. So what we're trying to show in both of these situations is that you have to be careful. Using Fermat's theorem, just because a derivative at some point is equal to 0 does not mean we have a maximum and minimum. What students are using is they're trying to use the converse. Just because you have a derivative being 0 doesn't mean you have a max or min. Now, if you have a max or min and it's continuous and differentiable, then we will have that derivative being equal to 0. Also, what's interesting is when the derivative does not exist, it's a point that we ought to be inspecting because it reveals something about what the curve is doing. Okay, so a critical number. A critical number is when the derivative at c is equal to 0 or does not exist. From the previous two examples, you can see those are points that we really want to look at. If f has a local max or a min, then c is a critical number. Now here's what we call the closed interval test. To find the absolute max and min of a continuous function, you first find the critical numbers, find the values of the endpoints, compare all of those values, and then decide who the absolute max and absolute min are. Let's take a look at this problem. So step 1 is to find the critical points, which means to take the derivative, and then find its values at those derivatives, and then compare it to the critical points. Now we have the graph right here, and here's the work. I took the derivative, set it equal to 0 because I want to know where those horizontal tangents are. It's at 0 and 2. And then here's my list of all the numbers that I want to look at. I want to look at the endpoints right here and those values, and then I want to look at the y values of 0 and 2. And then I make a decision on my absolute max and min. Now, they didn't ask me to find the locals, but I went ahead and put those in there anyway. Okay, you try this problem. Go ahead and stop the screencast and see if you can do it, and I'll show the answers. And here's the answer. I took the derivative equal to 0, it's x equal to 2, and then I compared it with the endpoints. Now this is a parabola, and you know that parabolas, the vertex is either a max or a min, and because the parabola is pointing up, the vertex is a min. So I hope you're not too surprised at what we're getting right here. This is at the vertex. Stop the screencast and do this problem. And here are the answers. Again, I took the derivative and I made my list and I compared everything, and I found my absolute min. There was actually 2 values, and an absolute max, which occurred at 3. And I think this was 66, not 6. 66, that was my absolute max.